How Did You Think I Would React? Is an episode of the Degrees of Freedom Project videos on chemical and thermal principles. Definitions and additional details can be found in the web page link in the description. The reactor models that are used to determine the fractional conversion and extent of reaction are, going from simplest to most complex, extent of reaction and fractional conversion models. The extent and fractional conversion are parameters given to you or specified by the problem. These models do not deal directly with either chemical thermodynamics or chemical kinetics. Chemical equilibrium models. These models assume that there is sufficient time in the reactor for the chemicals to reach chemical equilibrium. The extent and fractional conversion are calculated from the temperature, pressure, and feed concentrations of the system at equilibrium. Homogeneous chemical kinetics models. The chemicals are assumed to exist as a single homogeneous phase. The reactor models are based on the three idealized homogeneous chemical reactor models: the batch, the CSTR, pronounced C-star, which is basically a mixed or stirred tank reactor, and the plug flow reactor, PFR model. These use chemical kinetics expressions, feed conditions, reactor volume, and temperature to calculate the extent and fractional conversions. Heterogeneous chemical kinetics models. Typically, there are two or more phases in the reactor, such as gas-solid, liquid-solid, or gas-liquid. Gas or liquid reactants that are catalyzed on a solid surface are the most common. The models require simultaneous solution of chemical kinetic, mass transfer, heat transfer, and fluid flow equations. The extent and fractional conversion are calculated from the chemical kinetic expressions, catalyst amount, particle sizes, feed conditions, reactor volume, and temperature. These three videos, How Did You Think I Would React, Wishing Upon a C-star, and It's Totally Tubular, Man, introduce the third method with homogeneous chemical reactors. Earlier videos covered the first two methods. Heterogeneous reactions are reserved for the advanced videos or grad school. For these two videos, we are going to assume that there is a single chemical reaction, written as shown, occurring in the reactor. As a reminder, the nu sub i's are the stoichiometric coefficients for the reactants. Again, the stoichiometric coefficients are positive for products and negative for reactants. The most important thing in a reactor is the rate of reaction, or the reaction rate. Like the extent of reaction, its value doesn't depend on which reactant or product you examine. It is defined as 1 over the stoichiometric coefficient of the chosen species divided by the volume times the rate of production of the chosen species. If the reaction rate is uniform throughout the reactor, the volume, V, is the reactor volume. If the reaction rate varies with position, the volume V is a differential volume, and the moles of I are those contained within the differential volume. We also often use the reaction rate with respect to a given species, such as species A, species B, species P, or species S. This reaction rate depends on the chosen species. It is equal to the reaction rate times the stoichiometric coefficient of the chosen species. In chemical reaction engineering classes, by far the most often chosen species is species A, and the most commonly used reaction rate is that of species A. If you are reacting an aqueous solution, the mass density of the solution is unlikely to change with fractional conversion. If you're reacting ideal gases at a constant pressure and the overall stoichiometric coefficient for the reaction is 0, the mass density will not change. Also, if you have a constant volume batch reactor, the mass density will not change. In all of these cases, the volume in the rate expression does not change during the reaction and can be brought inside the derivative. Doing so results in the rate of reaction of species A being equal to the time derivative of the concentration of species A. This simplification makes the math much easier and is applicable to a great number of cases. We are going to derive our equations with this assumption. Note, while we limit ourselves to this case for most of the DOFPro videos, there are some advanced reaction engineering videos that do relax this constraint. Since the whole point of the kinetic reactor models is to get at the extent of reaction or fractional conversion, it makes sense to see how the extent of reaction is connected to the reaction rate. As usual, the extent is the final minus the initial number of moles, or output minus the input moles, of species I for the reactor, divided by the stoichiometric coefficient of species I. The time derivative of the extent is equal to 1 over the stoichiometric coefficient of species I times the time derivative of the moles of species I. For a steady-state reactor, the extent of reaction, with the dot, is the volume integral of the reaction rate. As a reminder, the integral mole balance on a species in a reactor participating in multiple reactions is the final moles of reactant I is equal to the initial moles of reactant I plus the sum over all of the reactions of the stoichiometric coefficient of species I and reaction J times the extent of reaction J. The differential mole balance on a species in a reactor participating in multiple reactions is the exiting moles of reactant I is equal to the entering moles of reactant I plus the sum over all the reactions of the stoichiometric coefficients of species I and reaction J times the extent of J. Each reaction also has a reaction rate for reaction J. And for a steady-state reactor, the extent of reaction J is the volume integral of the rate of reaction for reaction J. It's very common to analyze kinetics in terms of the fractional conversion of one of the reactants. The definitions have not changed. For an integral balance, the initial moles of reactant K minus the final moles of reactant K divided by the initial moles of reactant K is the fractional conversion of K. For a differential balance, the entering molar flow rate of reactant K minus the exiting molar flow rate of reactant K divided by the entering molar flow rate of reactant K is the fractional conversion of K. For a constant density reactor, the only type we're currently considering, the concentration of reactant K is equal to the initial concentration times 1 minus the fractional conversion of species K. In general, the rate of reaction is a function of the concentrations of the reacting species and the temperature at which the reaction is occurring. A great deal of time in a chemical reactor engineering class is devoted to determining these functional relationships. We will be limiting ourselves at present to relatively simple rate laws or kinetic expressions, where the concentration dependence will be the concentration of a species to some non-negative power, usually an integer, and the temperature dependence will follow the Arrhenius law. For elementary reactions and non-elementary reactions with fortuitous cancellations, the reaction rate usually has a form of the rate is equal to the forward rate constant times the reactant concentrations raised to some usually low integer powers minus the reverse rate coefficient times the concentrations of the products raised to some usually low integer powers. If the reaction is irreversible, the reverse rate coefficient is 0. For a truly elementary reaction, the exponent of a species will match the absolute value of the stoichiometric coefficient of that species, but in general, they don't have to match. An elementary reaction is one in which the molecularity of the reaction matches the stoichiometry of the reaction. It is common practice to refer to the exponents as the order of reaction. For an irreversible reaction of species A and species B, where the exponent on the concentration of species A is 1, and the exponent on the concentration of species B is 2, then we say that the reaction is first order in A, second order in B, and overall third order. If the order with respect to a species is not an integer, then the reaction is definitely not an elementary reaction. The rate coefficients, Kf and Kr, are functions of temperature. There are theoretical models based on molecular collisions and activated complexes that have a temperature dependence that comes from the model. However, experimental data are rarely accurate enough to warrant using these temperature dependences. Instead, the Arrhenius equation, proposed by Svante Arrhenius, a Swedish chemist, is most often used. The formula is the rate coefficient K is equal to a frequency factor, or pre-exponential, K0, times the exponential of the negative of activation energy. E sub A over RT, the gas constant times the absolute temperature. The value of EA and K0 can be found by measuring the rate coefficient at several temperatures and plotting the log of K versus 1 over T. The slope is negative EA over R, and the intercept is the log of K0. When dealing with gases, the concentration at constant pressure is a function of temperature as well, but the temperature dependence is normally regarded as being in the rate coefficient. With the concentration and temperature dependence of the reaction rate in hand, it's time to do a mole balance on a chemical reactor. Because moles are generated and/or consumed, we need either a generation or consumption term in the general balance equation. We normally call consumption negative generation, so the mole balance starts as the molar flow rate in, n dot J0, minus the molar flow rate out, n dot J, plus the molar generation rate is equal to the molar accumulation rate of dnj dt. The generation rate is the reaction rate for species J, R sub J, integrated over the volume of the reactor. So the general molar balance equation for a chemical reactor is n dot J0 minus n dot J plus the integral over the reactor volume of R sub J dV is equal to dnj dt. The next video, Wishing Upon a Sea Star, will apply this equation to the three idealized reactors, the batch, the sea star, and the PFR. The takeaways from this video are 1. The fractional conversion and extent of reaction can be specified as parameters determined from chemical kinetics or determined from chemical equilibrium, depending on the need. The reaction rate R is independent of species, and the reaction rate for species I is given as R sub I equals nu IR. 2. The extent of reaction is the volume integral of the reaction rate. The general balance for a reactor is n.j0 minus n.j plus the integral over the reactor volume of R sub j dV is equal to dnj dt. Thanks for watching. This video was brought to you by the DOFPro team.